This is problem 1, and I give you a list of standard reduction potentials. One for hydrogen, one for oxygen, one for zinc, one for copper, one for nickel, copper plus 2, zinc plus 2, nickel plus 2, one for bromine, molecular bromine, and one for manganese, 3 plus. And now, I'm going to ask a series of questions given that information. And given that information plus the knowledge that in order for anything to interact with the solvent, it has to be, in order for something to be oxidized by the solvent, its reduction potential has to be below the reduction potential for water. And water's reduction potential, the hydrogen reduction potential, is 0 volts. But we have to add to that an additional 0.6 volts for the kinetic barrier that exists. That's the overpotential. So in other words, for anything to be, so let's basically just detail for, in order to be stable with respect to reduction or oxidation by water. In other words, something in what materials will reduce water. Anything that's not stable with respect to being oxidized by water will reduce water when placed in water. Okay, the reduction potential. So if it must, the reduction potential must be above, my bad, above that. So anything that has reduction potential less than 0.6 volts when placed in water will be oxidized by the solvent, by the water. Okay, because this is the overpotential 0.6 volts. The water, the hydrogen is reduced at 0 volts. Hydrogen being the reduction, the product of reduction of water. And water is going to be reduce hydrogen. If anything that has reduction potential less than this, if the reduced form of that couple is placed in water, and the reduced form of the couple, for example, E, G, E naught, Okay. Zinc has a reduction potential of minus 0.76 volts. So will be oxidized by water, and this is under standard. Which is so the pH 0. So we're going to discuss it in terms of pH 0. At pH 0, you take a piece of zinc, you toss it into 1 molar acid, and it's going to dissolve. You'll see hydrogen bubbles come off. So zinc is unstable. But copper, for example, which has, we'll look at all the other things on this list. And sodium, which is the classic example, sodium or potassium or the alkali metals, the alkaline earth metals, they all have reduction potentials.
Was sodium 2 point what? Minus 2.71 volts.
Yeah, those are oxidation potentials. It's minus 2.71 volts, which is way below minus 6 volts. So you place a piece of sodium in water, what does it do? First, it's lighter than water, so it floats. And you've seen it, it fizzes around on the surface, it turns into a molten little BB that glows and fizzes around on the surface, giving vigorous, violent hydrogen, which eventually combines with the oxygen, you get a little explosion. Or if it does it nicely, just get a flame. Okay, so this explains why. With hydrogen, with zinc, you place it in water. Well, zinc is more dense than water, so it sinks and sits at the bottom and fizzes, in 1 molar acid. You get all these bubbles coming off. And so it is not stable in 1 molar acid. But as we've seen from our graph, which we drew earlier, and you should probably all make a copy of in your notes, as per instructions last time, as per instructions in the previous video. Zinc is stable in water at a pH of 7 because it's above the line. The line for water, E naught for hydrogen, or the voltage for hydrogen reduction, and for oxygen reduction both are such that E is equal to E naught minus 0.0592 volts times the pH. Okay? So as I increase the pH, I have to adjust and subtract 0.6 volts from that, and that line goes down. Well, zinc is above that line because the zinc doesn't involve any hydronium ions, and so it is a constant reduction potential. So zinc will be stable in pH 7, but in order to answer this question, we're only going to concern ourselves with pH 0 to make life a little bit simpler. Okay? So, given this background information, let's talk about which elements are stable in water. The other possibility of, in terms of redox stability is it could be reduced by the water, in which case it's going to oxidize the water. Well, for that to happen, it has to be above, in order to be stable towards being reduced by the water, it has to be below 1.23 volts, which is the oxygen reduction potential, plus 0.6 volts. Okay, and there aren't any elements with reduction potentials that would be 1.82 volts at pH 0. So unless you have a reduction potential of greater than 1.82 volts, you're not going to be reduced. And it'd be the oxidized form of that couple. would be reduced. And there's only one thing that I can think of, and that'd be the cobalt 3 plus, which is reduced by water. Beyond that, everything's pretty much stable in terms of being reduced by the solvent. So we don't really need to consider or to concern ourselves with that. I don't see anything in this couple. Look at the range we have here. Our highest reduction potential in the examples given, which are hydrogen, oxygen, zinc, copper, nickel, bromine, and manganese 3 plus. The range is from, the highest is 1.23 volts. That's oxygen. So, what, 1.51? Oh, 1.51, it's the manganese is 1.51, thank you. 1.51 volts, and that's the manganese 3 plus. That's not high enough above the reduction potential for oxygen to be effective. So the manganese 3 plus, that means it's going to be stable towards reduction. So the manganese 3 plus will not be reduced by the solvent. It's stable in water. Now, but this question, the first question is which elements are stable in water, and manganese 3 plus is an ion, not an element. So we have to look at the elements: bromine, nickel, copper, zinc, oxygen, and hydrogen. Okay, well, in order to be stable against oxidation, which is the one that's going to be the one that's going to be most relevant in these terms, it has to be greater than minus 0.6 volts. The only ones that are less than minus 0.676 volts is zinc. All of the others are above that. So all of the other ones, nickel, copper, hydrogen, and oxygen, are all stable in water as elements. Okay? That's what that means. So, question A, which elements are stable in water? Yeah. All except zinc, because they all have reduction potentials. Hydrogen's reduction potential, 0 volts. Oxygen's reduction potential, 1.23 volts. Zinc 2 plus is reduced to zinc, which is a reduced form, at minus 0.76 volts, which is below minus 0.6 volts. So zinc is the only one that's not stable in water. So the answers would be hydrogen, oxygen, copper, which the reduction potential is 0.34 volts, is stable. Nickel, with a reduction potential of minus 0.23 volts, is stable. Bromine, with a reduction potential of 1.065 volts, is stable. See how that graph's going to come in handy? Because it talks about all the different pHs. But as far as we're concerned, we're only interested in 0 pH. The answer is going to be hydrogen, oxygen, copper, nickel, and bromine. Those are the elements that are stable. Does that make sense?